Hello everyone. So today we are going to discuss achieving high throughput and elasticity in larger than memory store. So this paper was presented at VLDV 2021 by Chinmay, Badrish and Ryan. So how a typical data processing pipeline looks. We have lots of devices, sensors, IoT devices that generate a lot of data events, which goes through the stream processing systems, and then they are ingested in state management systems. And a lot of queries are being run on the state management systems. So what are the requirements of state management systems? They need specialized KV stores that can ingest as well as index events at about more than 100 million ops per second. And these events are to be gathered throughout the network, since event aggregation is required from various data sources. So other requirement is that they should scale across machines and cores, and it must be elastic because of n number of machines and servers. So what is the problem with existing high performance key value stores? They specifically rely on hardware acceleration, and they are not cloud ready. They store data in DRAM. They do not scale across machines. Adding scale support to these existing ones is not straightforward. Many statically partition records across cores to eliminate cross-core synchronization. This is an optimization for normal operations, but it affects migration and scale-out performance. Transferring records and ownership between machines and cores require head-stop approach kind of thing. So what are the goals of high-performance distributed key value stores? It should have a high throughput of the order of 100 plus million ops per second. It would be good if can use commodity cloud hardware. It has to tolerate failure and reconfig without hurting normal case performance. So the paper describes Shadowfax that they have built. So this is a distributed key value store over Faster. Faster is a high performance single node key value store. This transparently spans DRAM, SSDs, and cloud storage. Serves more than 130 million ops per second on a commodity Azure VM with standard Linux TCP stack. Has a unique approach of distributed reconfig by avoiding server-side key ownership checks and any cross coordination required during normal and data migration at indexing and network interactions. They say that it is able to shift the load in 17 seconds approximately, which leads to improving the throughput by 10 million ops per second. And when compared to the other existing approaches, that is C star plus memcached, they scale, or actually they provide 8x better throughput. So what are the key design decisions of Shadowfax? One is low cost coordination via global cuts, end-to-end asynchronous clients, partitioned sessions, shared data. So since it's built on top of Faster, let's go through Faster basics. So Faster is a lock-free hash table divided into cache-lined size buckets. Each 8-byte entry points to record whose key is hashed to that bucket. Each record then points to another record, forming a reverse linked list with common significant key hash bits. So each record is pointed by the hash table entry, and it's stored in the hybrid log. So they have per client application, per thread the thread is per CPU, which eliminates scheduling overheads. So each client thread can do operations like read, modify, write keys in Faster. So how it looks diagrammatically. So their hybrid log is divided into multiple regions the mutable region is where the records can be updated in place and it's in memory. Then they have a read-only memory which acts as a cache, and then uh, the other is the stable storage which would be there on any stable device like SSD, for example, and it's also log based. Like it's not in place, it's out of place update. So yes, so it also makes use of epoch based protection for uh, lazy synchronization or coordination. So how is that happening? So suppose we have multiple threads. In this case, we have 4 threads. Every thread has a local counter and there is a global counter. So a thread, so any epoch is said to be safe if all threads have their local counters or epoch greater than that epoch. So like in this example, this epoch 1 is safe when all the threads have epoch count greater than 1. And this thread 3 completes 1 at this point and it moves to epoch number 3. So it is safe. So generally safe epochs always lack from the current epoch, but they eventually catch up. So this was taken from Badrish CMU talk about this. The other way to visualize this that mentioned or diagrammatically represented in the paper is they have multiple threads. Each thread is per core, and then they visualize this in the sense like it's an asynchronous cut of operations going across threads where each thread has progressed independently of the other threads to create a view, and then they call it as an old view or a safe view, and then whatever operations happen after that cut are the new view. Going more into details of Shadowfax, it's a distributed key value store. So per server, they have a single faster instance. Clients can require clients do following requests. They they do upsert, they do read, modify, write. Records allocated on faster are in hybrid log as already mentioned. Each server has 1 thread per core. Faster instance is shared among all server threads. Client thread connect a session with 1 server thread where the record is owned by that thread. So sessions, so all the requests passed through the sessions are asynchronous requests. Then they would be bashed in the buffers to avoid software level the request dispatching. So the total the hash, I mean like records or hash range is partitioned amongst the servers. So hash ranges per server is associated with view number. Will in the later part of the talk will get to know why this view number is required. So there is also a metadata store. They in the paper mentioned Zookeeper, which keeps these metadata information of view numbers along with mappings of the hash ranges to the servers, and reverse mapping also they say that they keep. So view numbers are actually used to reduce the record ownership checks at the server in case of ownership migration, and they also enable lazy asynchronous progress through record ownership changes. So let's go through all those 3 principles, design principles. So the first one is partitioned dispatch and sessions. So yeah, to avoid cross-thread coordination, that happens by just having a single faster instance. So all threads come and they have a common key value store where they have to look up and do their operations. So faster differs cross-core communication to hardware cache coherence on the accessed record themselves. Threads pinned to virtual CPU have essentially two tasks to be done. They poll on network for new incoming requests, then for these incoming connections, and then for these connections, they poll for the incoming requests. Client threads are also pinned to CPUs and to avoid shuffling basically. And asynchronous, all requests are basically asynchronous. So this is how it looks. So on the client side, there is this library. So applications connect with the library, link with the library, and then create sessions. Sessions is like per thread, per client thread, and that thread is running tied to a core, and all the requests go through that. And on this side, on the server side, when the network layer receives, it passes to the core dispatcher to the relevant session that the client was communicating with, and they all hit the same faster instance. So basically there is no shuffling involved. That's their main idea. Then record ownership. So scale out and crash recovery are the two use cases where record ownership is changed and has to be dynamically provisioned. So, but the problem with that is it interfaces with normal operation. So clients send a batch to owner server, but then the ownership of those records or those requests which are in terms of record can change. So servers always need to validate before processing the request in terms of ownership. So that's where this view number comes into picture. So what happens is that when client creates a connection with the server, it also caches the view number of the server. And when it sends the batch of requests to the server, if they agree on the view number, that is if it is same, then the batch gets processed on the server side. But if it is not same, then server talks to the metadata server store actually to refresh its view number. It rejects the batch. Client on rejection, it also refreshes its own view number, and then it reissues the rejected batch. The reissuing of the rejected batch could be on the different session wherein the ownership had moved to some other different server thread. So the client session connecting to that server thread could be a different one. So it can be requeued, or it will be requeued to a different session. So that shuffling is there on the client side. So view numbers basically offload expensive hash range checks to client from server. So this is diagrammatically how it looks. So when threads on the server side get to know that the view has changed, they start rejecting requests. So then clients also understands that, and then it also goes through that same asynchronous cut kind of scenario wherein there can be requests asynchronously queued after the first reject as well. So that cut is basically till the time they have got the response, and all after rejects will be requeued later on to either the same or probably the relevant client sessions. So how this scale out and hash migration works? So they make use of global cuts to proceed in asynchronous phases. So transfer of ownership happens first, and then the records are moved. Both source and target go through a state machine transitions, and the first state is sampling. So what's the role of sampling? Sampling actually remaps ownership of hash ranges from source to target. It increments source and target's view numbers, registers a dependency between source and target in the metadata store, samples hot records by copying all accessed records to the hybrid tail, which is the memory region. And since these records are not yet at target, source and target till this point of time will keep on continuing to operate in the old ownership view itself. So the next step is prepare. So source sends a target, prepare for transfer RPC. When target, so till when the target receives that, it actually holds off the requests which are there on the migrating hash ranges until it has heard from the source to proceed, which it will in the later phases. So the next phase is transfer phase. In the transfer phase, source moves to a new view. It stops servicing requests on the migrating hash ranges, sends a transferred ownership message to the target along with list of all the hot records from the sampling phase. Then the target moves into target receive phase. Target inserts those sampled records into its faster instance, and it starts servicing these records of the migrated hash range. Then it's the migration phase. In the migration phase, source uses thread local sessions created with the target to send records in a parallel fashion of all these migrating hash range. So next phase is completion phase. In this, source sends complete migration to target, then source sets migration completion flag in the metadata store. Target, after receiving this completion migration message, sets its migration completion flag also in the metadata store. All the state transitions are essentially driven by source, since all the messages are being sent by source, and target just goes through its own state transitions. There is another thing that they have done is that they leverage shared storage for decoupling purposes. So migration cannot be complete until all records are moved to the owner. So Faster's hybrid records or log actually can be on the SSD. And to move these records, there would be IO involved, which would slow down, which would hurt throughput. So Shadowfax has a shared remote tier for this. What it does is it records all the local SSD records are eventually flushed to this remote tier. So source now can send an indirect record to the target indicating where that record location would be on the shared tier. So other aspect is how, so during these migrations and everything, a lot of indirect records can be generated. So how its cleanup is handled. So migration, yeah. So Shadowfax already does log compaction to eliminate its tail versions of the records from its shared tiers. So indirection record cleanup can be piggybacked to this thing as well. So talking about the evaluation, they have a couple of questions and I've just written short answers from their explanation. Does it preserve Faster's performance? They say yes, with negligible overhead. How it does compare to the alternate design compared to C star and with Memcached, they say that it is 4x better. Does it provide low latency? They say that 130 million ops per second is with 1.3 millisecond latency on a normal TCP, which drops to microsecond if it's a IDMA enabled stack. Then can it maintain high throughput during scale out? So they say that 10% hash range migration is with this migration, they are able to sustain 80 million ops per second. Do indirection records help scale up? Yes, because it restricts migration only to memory, and which essentially avoids IO. So it helps in their in the scale up. So do views reduce scale out impact on normal operations? So they say that views actually improve over hash validation for each request for ownership by approximately 17%. Can it scale across scales? So they were able to generate 930 million ops per second from 12 servers, around 800 threads and 2300 client sessions created. So this is the reference, and yeah, that's all from my side.